When asked in interview, do you know what is PMU or PMB? Do you know how a power management unit or block is interrelated or different from a power domain? To know all such question and answers, stay tuned till the end of this video. Hey guys, welcome back. In today's episode, we are discussing the below points. First, we'll do a general introduction. Next, we will talk about power delivery network, its significance. Next, we will jump into the concept of power domain. Next, we will explain the power management unit through infographics. Next, we will talk about the standard cells available for power management. In the same context, we will talk about the power switch cells, isolation cells, and retention cells and level shifter cells. So these are the standard cells used for power management. Finally, we will talk about the power management methods. This is the menu for today. Without any further delay, let's begin. Introduction. In SOC, more and more transistors are getting added and pulling to the risk of very high power dissipation in a die. So as per the Moore's law, many transistors are getting included in a chip as we proceed towards a lower technology node, and it causes the high risk of power dissipation. In the contrary, customers look for portable handheld devices having long battery life after a single charge. So you are quite familiar with this kind of handheld devices like your smartphone, PDAs, etc. Chips in mobile and handheld devices, advanced power management systems that can improve efficiency without sacrificing the performance. So just to fill the target that the battery life should be higher, we have power management systems inside the chip. This is done by adapting to the demands and constraints of particular workloads. Mobile, IoT or handheld devices usually often driven by unpredictable sensor or a user input. If it is a wearable device, it is monitoring like a smartwatch, it is monitoring your maybe your heart rate or something. So there is a sensor, right? Or user input. In case you are using a smartphone, the app you are operating by hand, so it is your user input. So these are the typical examples that you find day-to-day life nowadays. These have especially bursty workloads, right? Bursty means it has a lot of things to do once it is triggered with short period of high compute demand. That means whenever you trigger it, it demands for high computation through the processor, followed by long period of inactivity. This is the nature of the devices, whether it is your smartwatch or it is your smartphone or any other wearable devices, or maybe some medical devices that you are using. So there is a trigger. That trigger triggers a lot of activity in a burst, right? And then once those things are done, it goes for a sleep for a long time. So this is the typical type of nature that the devices have. Modern VLSI circuits integrated with a separate power management unit whose function is to manage the power distribution in the die efficiently. That means whatever we have talked about here and above, all these things should be manageable by the power management unit. This is the role of the power management unit we are having in modern days chips. So we are done with this particular slide. Let's move on to the next slide. Power delivery network, the significance. Here we will discuss about the significance of power delivery network. Now, what is a power delivery network? We will explain it through infographics here. The power grid in ASIC provides power to turn off or turn on any VLSI chips. So let us see it pictorially. That means with infographics. Here is our chip. So this is here our silicon lies, right? And here it's the boundary, right? You know it. Here it is drawn in with color, right? Let me point out sub parts of it. So this is the power ring, right? This one is the power ring and this is also the power ring. So if say this is VSS or VDD, say the another could be VDD or vice versa. Whatever kind of things you have, you can have this as a VDD and this as a VSS, right? So these are power rings. That means this one, right? This the thing that we are talking about here, or this one. Now, power strips are the sub lines which take up to the center of the silicon, right? This is a power strip and this is also a power strip. So this is a green color power strip and this is a red color power strip. So one is VDD, another one is VSS. Next, we have the IO pads here. We have IO filler. Here with the picture, you are getting familiar with the entire chip, how the things are there from a bird's eye view. Here is a corner cell and here is the core. This is where the silicon, we call it core. Power delivery network carries power towards the leaf cell such as standard cell, IP blocks or macro blocks. So you can see these power strips gets further subdivided into power strips. Power rings are subdivided into power strips and those carry the power up to the leaf cells, which may be standard cells, which may be IP blocks, which may be macro blocks. The power management unit resides in between the above mentioned leaf cells and the power grid to control the flow of the power. The purpose we have described in the previous slide already, why we have a power management unit. And remember here, the power management unit is abbreviated as PMU. Sometimes it is called power management block also. PMU decides and manages the power consumption through segregation known as power domains. How this thing works? It works through the power domains. So here we are done with the power delivery network and we have plunged into the power management unit and we will further plunge down into the power domains in the next slide. Here we will talk about the power domain concept, that is abbreviated as PD. Blocks which can be operated with the same power supply are identified and tied together like this. So here this is power domain 1 which have the power supply VDD1. Numerically VDD1 is different from VDD2 and here it is VDD3. So numerically these things are different, VDD1, VDD2 and VDD3. And operation wise this may be a digital block, this may be an analog block, this may be a macro. So I have colored them with different color. And here is our PMU or PMB, whatever we call it, the power management unit. This forms a power domain. So when they are tied together, this is a power domain PD1, this is PD2 and this is PD3. A particular power domain can be completely kept on or off irrespective of the neighboring block. So this could be on when this is off, right? Or this is on when this is off. So this way any block could be powered up or powered down. A power domain contains collection of design elements that share a primary power and ground supply net. So here you can see here the VDD and VSS will be same for all of the leaf cells here. Similarly here the VDD and VSS will be same for all the leaf cells inside it. Similarly the theory applies here too. The logic hierarchy level where a power domain is created is called the scope of the power domain. The scope of the power domains means this area. So this is the code wise concept. Generally we code this in UPF. So there the scope thing in terms of the code comes, you will find in the UPF series. There I have explained it with codes and examples and infographics. You can find that in the playlist. Any design element that belong to a power domain are said to be in the extent of that power domain. So these are typical terms you should remember when you are dealing with a power domain. So there is a scope, there is a extent. Okay, what these things are, you should be very much aware with these terminologies. So here we are done with the power domain concept and the power management block, that is PMB or PMU. And here are the power domains. So we have explained with the infographics and the text here how the power domain is there and how they are controlled. So these controls this and this. The power management block PMB or PMU controls all the power domains. Here we will explain the power management unit through infographics. Here is our PMU or PMB. First thing it does kind of operation is the isolation. Here what is performed in the isolation is the clamping of the output pre-sleep. So before sleeping it clamps the output. So this is called isolation. Retention. What does it retain? It retains the saved states. Once it is powered up again, it restores from the saved states. So this is the retention operation of the PMU or PMB. Next, it sends another kind of instruction which is called power down. What happens in power down? Shut down and wake up a block. So any block we have told you pictorially in the previous slide. So this is power down and next is reset. What we do in the reset instruction from PMU? Any block is in quiet mode pre or after sleep. So reset means that we reset the value, that means in a quiet mode. So these are the typical kind of operation, that means isolation, retention, power down, reset. Those are performed by the PMU or PMB. In addition, to manage the power, the PMU performs another thing, that is it suppresses the clocks during the sleep period. So the long period of inactivity is managed by the suppression of clocks. So these are the things that very technical with the PMU, and here we are done with this particular slide. So let's move on to the next slide. Standard cells for the power management. So in previous slide we have talked about different kind of operation. To enable this kind of operation, what we have to do? we have to use multiple pre-designed standard cells in our chip. What are those standard cells? Switch cell, isolation cell, retention cell, and level shifter cell. So these 4 type of different standard cells are used for power management. These standard cells are designed in coherence with the power management block or power management unit operations, so that whenever such instruction of switching or isolation or retention or level shifting is there, so that time this cell can operate in sync with the power management block. Now we will go in detail one by one of these cells. Power switch standard cell. Here is the picture. Here we have a power gated block and we have a header switch here. So this is a standard cell which is called the power switch cell, and it is placed at VDD, and hence it is called the header switch cell, and it is directly connected to the VSS, and there is no operation here. It is a direct connection, and here there is a switch. It is a header switch, and in case we want to do the operation, switch operation from the VSS, we have to give a footer switch. So this is another standard cell which is a footer switch, and here you can see this is a direct connection with the VDD, and this is the power gated block. These are the block diagrams for the switch cell, that is the power switch cell or the power switch standard cells. Now let us go through some description of it. To turn off power supply to a power domain or a particular time operation, that means for a particular duration, we need power switch to cut the power supply of the VDD or VSS to the domain. That means either we can cut from the VDD or from VSS depending upon how the instruction is coming from the PMU or PMB. Next, the switch cell is created within the scope of the power domain. So we have just shown you 3 power domains in last slide or last to the last slide. There we have talked about the scope. So that means the area of influence of the power domain. There we have to create the switch. The switch is either turned on or off as per the requirement. So that means it is as per the operation of the block. It is not as per the whims. It is as per the instruction set that are coming from the sensors or maybe coming from the user. So here we are done with the particular slide. We have explained the switch cells with the header switch and the footer switch for VDD and VSS, and we have gone through the detailed description of it. And let's move on to the next slide. Isolation standard cells. Here the power gated block is there, and we have a isolation cell. Here you can see it's AND gate representation, and we have a power up signal. So if we have a power up signal and the power gated is there, then only it goes to the always on block. Let us explain with text. When the power gating method is applied in a design in a particular mode of operation, we might end up with few on domains and few off domains. If the outputs of the shutdown domain are connected to the active part of the design, then it might lead to invalid signal transmission and crowbar current. So that means there is a block which is shut off and there is a block which is on. So this is off and this is on, and we have a connection, right? We have to isolate the two, right? This is done by the isolation standard cells. Otherwise, signal going from one block to another block will be misinterpreted with misleading results. To avoid this, isolation cell is placed on the output nets of a switched off domain, interacting with the active portion of the design. And this kind of cell, that means the isolation cell, is also controlled by the power management unit or power management block, that is PMU or PMB. So here we have done a brief description of the isolation standard cells. Let us move to the next slide. Retention standard cells. Sometimes it is called the retention flops also. So here is the schematic diagram of, or you can call it a block diagram. Let us start with some of the text. A retention cell is used to retain the data required in shutdown power domain. So that means retain. That means we have to do the save operation. A retention cell consists of flip-flops, and save latch has two control signals. One is the save, another one is the restore. When a block is switched off, that means it has been cut off and it is switched off, the states have to be saved, right? So that save instruction is coming from the PMU, and that has to be processed by the retention cell, that means this cell. And once the block is powered up again, the restore signal has to come from the PMU or PMB, and that has to be processed through the retention cell, and that has to act on the power domain. Save signal indicates when the data should be saved in the latch, which is just before the switching of the power. That means save is just when you are just cutting off the power, right? Before that, the save operation has to be performed. Restore signal tells when the data stored in latch, that means this latch, should be restored, which is when the power domain gets back to the active state. The state which is saved in the latch, that has to be restored back into the power domain with the restore signal, and the whole operation is controlled by the PMU or PMB with the help of the specially designed standard cell called the retention cell or retention flop. So here we are done with the description and the operation of the retention cell or flops. So let's move on to the next slide. Level shifter standard cells. Now first we look into some text. When two blocks power operated with different voltage level interact with each other, invalid signal transmission and crowbar current generation may take place. So that means two power domains, one with VDD1 and another one with VDD2. So these are two different VDDs and they are interacting, right? So their level 1, level 0 is different and the forbidden zone is different. So their interaction could be totally goofed up. Prevent this, we have the level shifter cells. To avoid this, the level shifter cells are placed in between the blocks with distinct voltage values. So the level shifter is a kind of cross-domain management or the cross-power domain management cells, specially designed in the standard cell library, which are operated and instructed through the PMU or PMB. Here is the graphical representation or the infographics, right? Let me give some description. Here PD1 operates at VDD equal to 0.8 volt. PD2 is with 1 volt. So low to high level shifter, LH level shifter is working from this to this direction. You can see with the arrow, right? And this is the level shifter cell or this is the level shifter cell. And here is the HL level shifter. That means high to low. High to low means VDD high to the VDD low. So this way the level shifters can be placed in between the communication path of the two power domains. So power domain 1, power domain 2. Now we just switch the high and low value in the next figure here, right? It is PD3 and PD4, right? Here the VDD is 2 volt and here it is 1.2 volt. So this is high and this is low. HL level shifter, that means high to low level shifter, is placed in this direction, and LH, that means low to high, is placed in this direction. In this way, the miscommunication between two different power domains which are talking to each other through voltages are done. The level shifter cells can convert high voltage level to low voltage level between power domains. That means cross domain talk here between the two different power domains are managed by the level shifter. That means the level shifter standard cell works as an interpreter between two different power domains for signal exchanges. Level shifters are placed on signals have sources and sinks. Level shifters are placed on the signals that have sources and sinks operating at different voltages. So this is a typical circuit concept of source and sink, from where to where a signal is going. So you will come across these terminologies when you actually involve in the VLSI design. We are done with the concept of the level shifter cells, and let's move on to the next slide. Power management methods. So here we will talk about various power management methods. Before starting that, let me just give you a brief. Whatever we have come across now will be implemented to the power management unit, and here we talk about some methods that typically is done at the very top level to the PMU or PMB. So first thing is the voltage management method. What we do in this, most common of the voltage management method is the dynamic voltage scaling, DVS. Here the circuit can statically or dynamically vary VDD depending upon the throughput requirement. Multi-voltage domain designs can also be classified under this category. So we have talked about multiple VDD domains, that is classified under the voltage management method. So these are methods, basically typically methods of managing the power to the PMU or PMB. Throughput management method. Dynamic frequency scaling, DVFS, is one of the most used methods in this category. CPU frequency scaling for battery-powered computers is examined in terms of its impact on battery life, system performance, and power consumption. This method ensures efficient use of battery without compromising the system performance. So you can see there are different approaches of saving the power. One is the voltage management method, another is the throughput management method, which is also can be categorized as DVFS, that is frequency scaling, right? And next we talk about the functional management method. Here, what we do, we have an alternate design with implementation method that consumes less power to a separate design, maybe from a different FSN. So there we have the less power consumption method. in that design. Some of the low power design techniques such as low power FSM design, bus encoding, gate reordering, battery aware dynamic task scheduling represent these kind of cases. So these are very advanced things. As you plunge deep down inside the VLSI design, you will come across all these methods. So I have touched base the different methods of power management that are practically done on the portable and wearable devices. Here we are done with the particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislike, put that as in words in the comment section down below. And bye for today.